Hello everybody, and welcome to the continuation of problem 7 on our list of final exam review problems. In this video, we're just going to be looking at part B of this exercise. And let's remind ourselves what we're given here. So we've got a linear transformation from P2 of R to P2 of R. We've got two bases for P2 of R, beta and beta prime. Okay, we're given what beta is, and we actually figured out what beta prime was in part A. And the only other information that we're given relevant to part B is this. Okay, they tell us what we get as outputs if we plug in P1, P2, and P3. Okay, now to address the question of invertibility, there are a lot of different ways that we could do it. The tack that I'm going to use is to start by noticing that these three output vectors that we get, those are actually linearly independent polynomials in P2 of R, and there are three of them. Okay, and we need to demonstrate that that's true, but if it's true, it's telling us that we kind of have enough outputs. There are three of them in a three-dimensional space. We've got enough outputs to generate everything that's in P2 of R, which means that there's some evidence that this function t is onto that we've got here. Okay, that's going to be the tack that I'm going to take here. So to get started on that problem, let's see if we can convince ourselves that those three circled polynomials are linearly independent. We can do that by direct calculation. Okay, so let's start our argument. Okay, so our claim is that the set, we just call S the set of these three outputs that we're getting. We're going to claim that that's a linearly independent set. Okay, we'll go a step farther and actually claim that that's a basis for P2 of R. Okay, and a basis has two properties, one of which is linear independence. So let's start with the linear independence part of this. Okay, so to see that this is the case, we're going to take a linear combination of our polynomials in this set and set them equal to 0. That's kind of the starting point if we want to convince ourselves that a set is linearly independent. Okay, equals 0. Okay, we'd like to convince ourselves that that equation star has only the trivial solution. Okay, well, this goes back a little ways in the course, but that equation star is equivalent to a system of equations. If you rearrange it, get all of the like terms together, equation star is equivalent to the system looks like this, 0, 0, 1. I'll kind of leave it to you to confirm this. Okay, that this system of equations results directly from equation star that we have up here. Okay, and if you go ahead and do row operations on this and reduce it down to an echelon form, you come down to here. Notice that we've got a pivot column, or a pivot in every column in this case. And we mentioned way back earlier on in the course that if you set up this system and you discover that there are no free variables, then the only solution that you can have is the trivial solution, and that's equivalent to the linear independence of the vectors in the set S. Okay, so we might just make a remark. Since this system has only the trivial solution, we know that the set S is linearly independent. Okay, so we're halfway to a basis. Basis needs to be linearly independent and to span the space. But do we really need to show that that set spans P2 of R? Not really, because we know what the dimension of P2 of R is. It's equal to 3. So we've got a linearly independent subset of vectors in a three-dimensional space. Now comes corollary 2 to the replacement theorem to tell us that we really have a basis here. Okay, so since the dimension of P2 of R equals 3, by corollary 2b, that S is a basis for P2 of R. Okay, so we've established our first claim that this is really a basis. Okay, and like I said, there are different ways to the end of this, but knowing that this is a basis is a huge piece of information if we find the right theorem. Turns out that theorem 2.2 fits really nicely here. You can look back maybe on your theorem sheet and see what that's saying. Okay, so theorem 2.2 gives us a way of calculating the range in terms of the span of in our case T of beta prime. And I'm really just copying down what this theorem is saying. But T of beta prime, what is that? Okay, well, the vectors in beta prime were P1, P2, and P3, so T of beta prime is exactly these three vectors up here. Okay, just by directly from the information that they gave us in the problem. So this is the span of S. And what did we just show about the set S? Well, we showed that it's a basis for P2 of R, so its span has to be P2 of R. So we've just demonstrated that the range of T is all of P2 of R. By definition, that's what it means for T to be onto. Okay, but what were we being asked to show in this problem? We've done a lot of work. It's kind of easy to lose track of where we're trying to go with all of this. We wanted to show that T is invertible, or actually they asked us if T is invertible. Turns out the answer is going to be yes to that. Okay, so showing that it's onto is kind of halfway there. We also need to show that T is 1-to-1, but if you look at our linear transformation T, notice that the domain and the codomain are the same. So if you think back to theorem 2.5, it says that if the domain and the codomain have the same dimension, then if your function is onto, it's also 1-to-1. Okay, so without even doing anything more here, we know that our function is also 1-to-1. And that completes the proof, essentially. Okay, and so T is invertible. All right, and we're done.